Okay, I'm going to go through lecture 4 on vector algebra. Here's the content of all the lectures. We're now up to vector product. This is the second type of doing multiplication with a vector. And we'll see that we'll be able to calculate moments of forces and areas for two examples. List of the learning outcomes for this module. Multiply vectors, and we'll see the geometric and Cartesian format. We'll use the determinant method for calculating based on the components of the vectors, and look at laws of vector multiplication and examples of what we can get out of vector the vector product, moments of forces and areas. And we're going to look at some example engineering problems. Let's just briefly remember the scalar product. Remember, this is a way of multiplying two vectors together. We call it the dot product because they're linked with a dot, and we just, in terms of components, multiply each component and sum them, and the result is a scalar. We can also write it like this. So we have the two magnitudes of the two vectors and the angle between the two vectors, so we can equate these. And one of the useful things is to calculate the angle between two vectors. A squared, or a dot a, is a squared, is the magnitude of a squared, straightforward, and a dot a does not exist because you can't multiply dot product, scalar product, three vectors together. A dot b minus c equals 0 doesn't mean that b equals c. We need the normal rules of arithmetic don't apply, so you have to be careful about that and understand what it really does mean in terms of vectors. Let's have a look at an example of the scalar product, the dot product, for doing calculation. Now this is quite an involved example, but it actually sums up what you can do with vectors in a practical sense. So we've got a setup here. We've got a bar sticking out of a wall, cantilevered, and it's supported by three cables, 1, 2, so A to B, A to C, and one from the middle, D to E. We want to find the vector force on each of those three cables. Now we've got forces on the three cables of 400 newtons, 400 newtons, and 350 newtons, but what's the vector of the force in those directions? And that's one thing we can get. So the general equation for a vector, given some direction in terms of direction cosines, and the unit vectors is this, and we can work out these direction cosines from the geometry here, and that can be written like this. So cosine of A is x over r, where r is the length. So we can write that AB magnitude is 38, root 38, AC is root 35, DE is root 13, so those are three magnitudes, lengths. So the force vector B, that's A to C, going along A to C, is 400 times the vector of AC, which is minus 5 to 3, divided by the magnitude. And similarly for C, it's actually the same size, but we've got a minus 2 here because we see it's symmetric about that centre bar. And E, FE, It's 350 times the vector minus 203. Sorry. Minus 203. Yep. Right. Now we're going to move on to the vector product, also known as the cross product. It's the second type of vector multiplication. It's a vector and the vector product of two vectors A and B is defined as this, and it's written with a cross. That's why it's sometimes called the cross product, and I'll use those two terms interchangeably, vector product or cross product. And this is defined as the magnitude of the two vectors times by the sine of the angle between them times by a unit vector n. Now this is written as n because it's a normal, it's a unit vector in the normal direction. So what it turns out to be is that this vector product results in a vector which is at right angles to A and B. And this is super useful in terms of geometry. So theta is the angle between A and B, as you may expect, and as I've said, n hat is a unit vector normal to both A and B. So let's see what that means. If we've got A and B in a plane, then n hat, the result of A and B, the vector result will be a vector normal to that plane, which turns out to be extremely useful in geometry. Remember, we've got a right hand rule. Take your right hand, thumb pointing upwards, your fingers curling around the axis from X to Y, Z, your thumb points in the Z direction, so X, Y, Z, A, B, N. If you point the other direction, A to B, the result would be down. N would be down. That's the right hand rule for vectors. The vector product form an orthogonal right-handed set. Remember that the result of a vector product is a vector, not a scalar, so it's called a vector product. So A cross B gives you a vector n, and it's an orthogonal right-handed set, a bit like the XYZ axes of a Cartesian system are an orthogonal right-handed set. So from this definition, only the order of multiplication matters. Vector B cross A is the opposite direction to A cross B. So we can write this down. A cross B equals minus B cross A. Useful. So one particular thing in mechanics for the vector product is we can work out the moment of a force. If F is a force vector and R is a position vector of a point which F acts through, so here P, position vector of O, then we can work out the force. Sorry, we can work out the moment due to the force about the point O. Okay. F passes through point P, vector OP is R. Perpendicular distance from O to R is R sine theta. That's on there, R sine theta. So F times R sine theta would give us the moment. Which is that? Which is very similar to the cross product, the vector product. But as n is a unit vector, we can actually ignore that when it comes to the magnitude, because it's simply 1. Okay. M is equal to R cross f, rf sine theta. Let's look at an example. So we've got a arm, literal arm, pulling on the bar of a crank, trying to turn the nut. We'll see that if it's pulling, the perpendicular distance here is here, and what was r in our last diagram was the length of the crank. So d sine theta is the lever arm that's normal to the force. So the moment required is df sine theta, and is a unit vector in the direction of the normal to the plane. So n is going to be acting vertically upwards in this case. So although we get a vector out of the cross product, we actually don't use the vector direction unless we need to, and we don't need to when we're calculating moments. So let's write this down again. M is R cross F, which equals R cross F sine theta. M is a vector in the direction normal. Moments add by the parallelogram rule, as do all other vectors. They add by the triangle or parallelogram rule, which are both equivalent. This method of calculating moments via the vector products is very useful when it comes to 3 dimensions. We can see all these vectors in 2 dimensions quite easily, but when it comes to 3 dimensions, it becomes extremely difficult. So, for example, if we've got 3 forces acting at the ends of at points on a structure, for example, in 3 dimensions, we can calculate the 3 moments and simply add them as we would do normal vectors, and we get the total moment. Extremely useful. One other thing we can do with vectors and the cross product is calculate the area of a shape, area of a parallelogram. So you know that the area of a parallelogram is the height times the length, and the height can be calculated as AD sine theta, or vector A sine theta. So cross product gives us that area. Cross product of 2 vectors and the sides of a parallelogram. Now, a parallelogram, not the most common shape we get, but we can do the same for a triangle. It's simply half of that parallelogram calculation, and we can make up all sorts of shapes with triangles and approximate curved surfaces, domes, for example. So extremely useful. Particular laws for the vector product or cross product. So it's anti-commutative. We've seen that. A cross B equals minus B cross A. Because of the right-handed rule, the result is a vector in the opposite direction when you change the orientation of the axes. Let's play that little animation at the bottom here. Okay. Non-associative, so we can't expand brackets, and we could with a vector product, a scalar product. So we cannot expand A cross B like that. We can do the vector cross product, three vectors, but we can't expand them like normal arithmetic. Vector BC is perpendicular to both B and C, and thus the vector plane becomes perpendicular to the plane containing B and C. So A cross B cross C must be in the plane containing B and C. However, A cross B cross C is in the plane AB. So A cross B cross C and A cross B cross C are different vectors, so we must always use the vectors for the brackets for the vector product. Distributive law, well, this is quite handy. We can use expand brackets out when we're multiplying by a scalar, and similarly, slightly less obvious, we can multiply brackets out when we have addition in the brackets of vectors. And we'll see an example of this a bit later. Parallel vectors. So by the definition of the vector product, A and B are parallel. If A and B are parallel, then theta is 0. Right? Because we've got a sine of angle between the vectors. So A cross B equals 0. Sine 0 is sine 180 is 0. Thus, if A cross B equals 0, either A or B equals 0 or A and B are parallel. And we need to check whether A or B are 0 or not. If A cross B equals A cross C, then we can't deduce that B equals C, because we need to check that A is not 0. And second check, which is not as obvious, is that A is not parallel to B minus C. The unit vectors are really important here, because they themselves form 3 orthogonal vectors. But let's look at the squares of each unit vector. I squared equals J squared equals K squared in terms of cross product. So I cross I equals J cross J equals K cross K equals 0. Theta equals 0. So sine theta equals 0. And because of orthogonality, we get the normal vectors. I cross J equals K, J cross K equals I, and K cross I equals J. Again, this is quite a nice result. We cross them the opposite direction, opposite way, we get a negative. So J cross I equals minus K, K cross J is minus I cross K is minus J. Again, this is quite useful, certainly when we're doing planar geometry, trying to find points and normal points on a plane, vectors normal to that plane. Have a look at those 3 axes, see if you recognise why these are as they are. We can expand the Cartesian coordinates to show what the vector product looks like in Cartesian terms. So we've got to expand the three vectors, multiplying each, and you know how to multiply brackets out with multiple things, and it looks like this. It's getting quite large. If we expand it out a little bit further. Okay, quite useful here. We've got these I's and I cross J's and I cross I, so we can see that those 3 are going to be 0. So A cross B in vector terms can be written like this, and then further simplified to give us this cross product as something which is a lot simpler, but not necessarily easy to remember. How do you remember that? Well, there's various tricks and tools you can use to remember this. in an exam you'll have probably have a copy of this in your slides, but it's certainly useful to remember that. So one way of remembering this is the determinant method, or so-called determinant method. And if you've done any matrix algebra previously, you'll have done determinant, and you're going to, on this course, do matrices later. However, let's just have a look at what we mean by this determinant matrix. So to calculate A cross B, we would write a matrix with the three unit vectors, I, J, K, and the two vectors that we're crossing in components written down. Now, to calculate the determinant of a matrix, something like this, we do the letter in the first column, then we, as we've done here, we sort of eliminated that row and column, and we're left with A2, A3, B2, B3. Then we do, for the second column, it's minus, because in determinants it goes plus, minus, plus. So minus J, and then we're left with A1, A3, B1, B3, A1, A3, B1, B3. And the third column is plus K, and then we're left with A1, A2, B1, B2, A1, A2. And then, so we're in this, now on this second, we've now got these three smaller determinants, and to calculate the determinant of a 2 by 2, we multiply the cross diagonals and subtract the other cross diagonals. So A2 B3 minus A3 B2 times I, minus A1 B3 minus A3 B1 times J, plus A1 B2 minus A2 B1 times K. Now you may think that's not easy to remember, but as soon as you start doing vectors, matrices, you will find that is easy to remember, because it's fundamental in your matrix arithmetic. So there's one way of remembering the cross product. Let's have a look at a vector product example. Right, we're given three vectors. Calculate P cross Q, P cross R, and Q plus R. So this is good practice for doing your determinant calculation. We write the determinant in terms of I, J, K, and then the two vectors P and Q. We expand that, we get a vector. P, Q cross R, we write the determinant, we expand it, we resolve it further, we get a vector. Q plus R is 204. P times Q plus R comes to be 4 minus 10 minus 2. We can expand that bracket. Quite an easy calculation to do now when we see that those two are the same as we'd expected from the rule. So it shows that vector multiplication is distributive over addition. Okay. Let's have a look at another example. So force acts the end of these triangular brackets. Right, there's the force acting down here at 30 degrees, magnitude 400 newtons. Determine the moment of the force about the point O. Okay. This will be quite tricky in Cartesian geometry, but let's have a look at what we'd do. So the moment is 400 sine theta sine 30 times 0.2, 400 cos theta times 0.2, so the moment is going to be 96.8 newtons. Let's do it in vector arithmetic. So R is the point of action for, so looking down here, 0.4 minus 2. And we can write the force vector. And the moment is multiply the two forces together using a cross product as the determinant, and we can expand that. So vector cross product is defined by this. It can be calculated using a determinant method. The vector product is itself a vector, so order matters. Vector product can be used to calculate moments, as seen in the examples.